Vamos a comenzar. La semana que viene no hay clase. Es para términos de la universidad, es viernes. Entonces, comienzo teoría de la firma hoy. La voy a terminar el próximo miércoles, que es el 3. Y luego el 10. Hay básicamente un repaso con problemas de teoría de la firma. Y luego ese es la material para el primer examen parcial. Okay. Eso quiere decir que el examen sería como el 17 o el 23, dependiendo qué decidimos. Si vamos a cubrir material del segundo examen parcial antes del examen o no. Okay. Let's start. The last few times we derived a Marshallian demand curve, and we did a bunch of algebra, and we used a Cobb-Douglas utility function, and we got our demand curve. We saw that it was going to be downward sloping. We also derived an expenditure function, right? And an indirect utility function. Okay. So working with the demand curve, I wanted to find something known as elasticity. In general, and this applies to any two variables, if I have a percentage change in a dependent variable resulting from a 1% change in another variable, an independent variable, that's known as elasticity. Right? For our purposes, demand, it's right. If I have, excuse me, a percentage increase in price, right? How much does quantity increase in percentage terms? That's demand elasticity. So, like I said, we've seen how the demand for the ith good, right? We have a bunch of goods, depends on the price of all goods and incomes. That means the price of all the other goods, the price of itself and income. Since there are too many variables, and prices and income, I'll assume, except for the ith good, all prices or income are held constant. You know, that's how we do our partials, right? We hold everything else constant, and we focus on the change on just one variable, right? So we draw our demand curve. In this case, it's a bad graph, but suppose I have two individual demand curves. This is for one person, this is for another person, and they're all in the market. All I have to do is sum them up horizontally. At this price, this guy demands this much. At this price, this guy demands this much. I add them up, both, and I get a new demand curve called a market or industry demand curve. It's as simple as that. I just add up all the individual demand curves to get a market demand curve. Okay. So market demand curve, XI, depends on the ith price, on the price of all of the goods, and the whole distribution of income. If I change who has the income, demand's going to change, simply because people have different tastes, right? If all the rich people really love vanilla ice cream, the demand for vanilla ice cream will be high. But if I change the income and all of a sudden the rich people don't like vanilla ice cream, that'll change the demand for vanilla ice cream. So demand, right, for product X depends on its own price, the price of all the other goods, and the distribution of income. So we have that downward sloping demand curve. I take the partial with respect to its own price to get the slope, right? So that's what I have here, the slope of the demand curve. The problem, however, with using slope is that it's unit sensitive. Oh, before I move on to that, I forgot. For example, if the demand curve is very flat, a small change in price will result in a big change in demand, and vice versa if it's very steep, right? A small change in price or it would take a large change in price to get even a small change in demand. And as I said, the problem with slope is it's unit sensitive. The example I use here is if I measure demand for something that we sell by the pound, if I measure, or by weight, if I measure it in pounds per dollar, right, US pounds per dollar, right, the slope is going to be different than if I measure it in, the example I have here is grams per yen, right? So if I change one of the units that I'm measuring in, the slope will change. And we want something that doesn't change that way. So we come up with elasticity. In this case, it's the percentage change in the quantity demanded for Xi divided by the percentage change in the price of Xi, Pi, right? And I can write that, right, as the change in Xi over Xi divided by the change in Pi over Pi. That's unit free because that's in percentage. So it doesn't matter if I measure it in grams per euro or pounds per dollar. A percentage change is going to be the same when we have a change. Now, in general, right, for demand, this is going to be negative because the slope is negative, and an increase in price will decrease demand or the quantity demanded, and vice versa. For the most part, in most textbooks, what they do is they present it in absolute terms, simply because it's easier to think of it in absolute terms, right? The number goes up, elasticity goes up. So here it is. And basically, I just take this right here, right, and rewrite it. I bring the Pi up top, the Xi to the bottom, so I get the change in Xi over the change in Pi times Xi over Pi. And that's what I have here. I have Pi over Xi times the slope, the partial of Xi with respect to Pi. Did you guys want me, should I go through the algebra there? Are we good? Does it make sense? Are you nodding it makes sense, or are you nodding I should go over it? Over it. Okay. So I have the change in Xi over Xi over the change in Pi over Pi, right? Basically, this is an I, by the way. I bring the I down, so I just rewrite that, and I bring the Pi up. So I have Pi comes up to the numerator, Xi goes down to the denominator, and here I have Xi change in Xi over change in Pi. That make sense? The algebra good? Okay. And that's basically what we have here. But instead of having the big changes, I change it to partials. But it's either way, that part of the elasticity formula is just a slope. Okay. So suppose I have a demand curve, a linear demand curve. That means it's a straight line. The elasticity of the demand curve up at the origin, up at the intercept here at point A, right, is going to be small. In other words, very inelastic, and we'll talk about those terms in a second. Whereas down here at B, the number is going to be very large. So that's because at B, a small change in price results in a small change in demand, and A is high because a small change in price leads to an infinite percentage change in demand. And then down here in B, it's almost essentially zero. So with the linear demand curve, the elasticity changes throughout the demand curve. That's true of most demand curves, even nonlinear ones. But you can draw a constant elasticity demand curve, but it takes some doing. And then somewhere in the middle, elasticity is going to equal 1. And that's basically where a 10% change in price leads to a 10% change in quantity demanded. And in this case, we'll call that point C. Oops, a little faster than I wanted. So back to the algebra that I did here on the board, right? So in general elasticity, and this, it doesn't matter if it's demand elasticity, we're going to learn about cross elasticity, income elasticity, point price elasticity, which we just talked about, elasticity of supply, whatever it might be, two goods. I have a percentage change in one good, the dependent variable, we'll call it Y, divided by the percentage change in X. So I can rewrite that the way I did is a change in Y over the change in X times X over Y. Right? So this applies to demand as well as supply. I can apply it to any dependent variable that's affected by an independent variable. So going on, I just change the big deltas, right, down here and turn them into partials, and I get something very similar to our point price elasticity of demand. All I have to do is change the quantity demanded for Y and the price for X. Now that is known as point elasticity because it's elasticity at a point on the curve, depending on what curve it is, supply, demand, or whatever else. But it's a point. The other measure of elasticity is called arc elasticity, and it's a measure, an average measure of elasticity of a range through the curve. Right? So arc elasticity is a change in Y divided by average Y over the change in X divided by average X. So algebraically, right, I have 2 points, Y1 and Y2. So it's Y2 minus Y1 divided by the average, Y2 plus Y1 divided by 2. All of that divided by the points of X. That's X2 and X1. So X2 minus X1 divided by the average of X. So that's X2 plus X1 divided by 2. Of course, the 2's cancel. And I write Y2 minus Y1 as a change in Y, and X2 minus X1 as a change in X. So I get the change in Y over the change in X times X1 plus X2 divided by Y2 plus Y1. Right? And it's just a different measure of elasticity. Instead of measuring elasticity at a point on the curve, you're doing it through a range. There's really not much to gain conceptually from using arc elasticity. It's mainly algebraic, so for the most part, we're going to concentrate on point elasticity for the rest of the class. So our definition, price elasticity of demand, the responsiveness of the quantity demanded to changes in the price of a product, holding constant the value of all other variables in the demand function. Right? That's the price of all of the goods, income, etc. Right? We're going to denote this as epsilon P. Remember, epsilon P is going to be negative since the demand curve is downward sloping. For our terminology, if I take epsilon P or the elasticity in absolute terms, if it's greater than 1, we say it's elastic. That means that a 10% change in price gives me more than a 10% decrease in the quantity demanded. If it's unitary elastic, that means elasticity is equal to 1, so the absolute value of epsilon P equal to 1. That means a 10% increase in price gives me a 10% decrease in the quantity demanded. And finally, inelastic demand, epsilon p less than 1, or the absolute value of epsilon p less than 1, that means a 10% increase in price leads to less than a 10% increase in the quantity demanded. If we're talking about just price or a change in price, if I increase price when I have elastic demand, I get a decrease in revenue. If I change price in any direction, if I have unitary unitary elastic demand, I get no change in revenue. And finally, if it's inelastic demand, if I increase price, I increase revenue because the quantity demanded changes by less than the quantity, by the, excuse me, less than the percentage change in price. Now that's different than if I change quantity. If I change quantity, it's just the opposite, which makes sense because one's in the numerator, one's in the denominator, as far as algebra. So with elastic demand, right, the change in price changes the quantity demanded by a larger percentage than the change in price. This means that every time I increase price by 1%, the quantity will decrease by more than 1%. Therefore, revenue, P times Q, I think we've defined that already. If we haven't, revenue is price times quantity. It's fairly simple. So revenue will decrease since the increase in price is less than the decrease in quantity demanded. Of course, the opposite happens with inelastic demand, and with unitary elastic demand, revenue remains unchanged. Okay. Questions? There are other types of demand elasticity. The one we've been talking about is own price elasticity, and in general, point price elasticity. That's just a percentage change in the quantity demanded of Xi divided by the percentage change in its own price. Another type of elasticity is known as cross price elasticity. That's the percentage change in the quantity demanded of Xi divided by the percentage change in the price of another good, right? So for substitutes, right, this would be positive. For complements, it would be negative. If you guys remember what a substitute and a complement is. And finally, income elasticity. The percentage change in the quantity demanded of X divided by the percentage change in income. So if income increases, if it's a normal good, income elasticity will be positive. If it's an inferior good, it would be negative. So we'll start with cross price elasticity since we've already done own price elasticity. We've talked about it quite a bit, right? It's a responsiveness of demand for one product when the price of another product changes, or the percentage change in Xi divided by the percentage change in Pj, where J is another good that's not I, but related. So we've already actually talked about this when we talked about the income and substitution effect. But substitutes are related products for which a price increase in one leads to an increase in demand for the other. You can get the positive relationship. And complements are related products for which the price increase in one leads to a reduction in demand for the other. So for cross price elasticity, if they're substitutes, the cross price elasticity is going to be positive. If they're complements, it's going to be negative. And of course, if they're independent, if they're not related, it's going to be zero. Next is income elasticity. Did I go too fast? Okay. It's a responsiveness and demand changes in income, holding all other variables constant. So when income changes, how does demand change? Holding the price and anything else that might affect demand constant. We do the same algebra as we've done before, right? And I get the partial of xi with respect to I times I over xi. And by the way, we can do the same thing for cross-price elasticity. We just change I for pj. And in general, we can think of income elasticity in two ways, and they're both related. We know what an inferior good is. So an inferior good, product for which consumer demand declines as income rises. Therefore, inferior goods have an income elasticity which is negative. We can also think of those as counter-cyclical when we talk about the macroeconomy, i.e. when things are going good, we buy less of this product, the inferior goods, because we're richer and we're buying other products. A normal or superior good, on the other hand, has excuse me, has an income elasticity that is positive. For normal goods, in general, we think of the income elasticity being between 1 and 0, right? And for macroeconomic trends, that's basically non-cyclical. In other words, the demand for that product doesn't change much. Buenas noches. The demand for that product doesn't change much, right? When we're in recession or when things are going good. Basically, we buy the same amount most of the time. It's a normal good. Next, we have superior luxury goods, and they have an income elasticity that's greater than 1. Right? That means when our income increases by 10%, our demand for that product increases by more than 10%. That means when things are going good, we buy a lot more of this product. When things are going bad, when recession, whatever, we buy far less of this product. For that reason, we call it pro-cyclical. Okay. Other measures of elasticity, and there are a lot more than I can mention. Advertising elasticity, that would be the percentage change in the quantity demanded divided by the percentage change in advertising expenditure. So if I increase advertising expenditure by 10%, how much does the quantity demanded increase? If it's, of course, more than 10%, income elasticity, right, is greater than 1, less than 10%, less than 1, of course. If it's exactly 10%, it's 1. Weather elasticity, and this can be measured on different scales. There's something known as dry bulb temperature. Basically, it takes into account temperature and humidity. And for certain products, it's very important. For instance, electricity, home heating oil. There's also other measures, precipitation, for instance. I'm sorry? Yeah. So if you're up north in the winter, right, the precipitation could be snow, or even down here it's rain. So those things will affect people going to the mall and shopping, those kind of things. Or even when it's really hot, people like to go to the mall, movie theaters, just to get out of the heat, to be in the air conditioning. Interest rate elasticity. This is important for durable goods, stuff that we have to take out loans for to buy, washing machines, stoves, cars, etc. And it tells me how much the demand for that good changes in percentage terms when interest rates change. Questions? Okay. Now, if you remember 2 classes ago, we derived, and we did this, we actually used this last week too. We derived a Marshallian demand curve, right, from a Cobb-Douglas production function. And what I'd like you guys to do is basically to derive the elasticity, right, of this demand curve. So the first thing I want you to do is go ahead and derive its own price elasticity. And here, let me write it down over there. So basically, from that formula, I would like you to derive the elasticity of demand. Okay. I don't see anybody writing. Okay, what's the first thing we have to do? I'll give you a hint, I'll point at it. En este caso, sí. So I take the partial, I hold everything else constant except.
PX, y entonces después despejas para PX, lo sustituyes ahí y la X ya está despejado.
All right, so what is it then? What's this leave demand? My price was this leave demand.
Bueno, vamos a sacar la parcial que sería negativo I sobre 1 más beta sobre alfa, y eso es cuadrado, ¿verdad? Dividido de X al cuadrado. Entonces ya tenemos la parcial, lo multiplicamos por PX, que PX sería.
Okay. Does everybody see what we did there? Okay. Now, in general, when I ask you to calculate elasticity, I'm going to give you one of two things. I'm going to give you a formula, and if I give you a formula, this is what we're going to do. All right. If I give you changes, percentage changes, you go back to the original formulas that we had at the beginning of class, and I don't even have to, just percentage change in X over the percentage change in Y. And that's much simpler. Okay, so now we derived, I didn't simplify. Here I have Px squared, here I have Px, one of the Px was canceled, and that's what I did. So this is our own point price elasticity formula of demand. The next thing I would like you guys to do is to derive income elasticity. So, going back to our original Marshallian demand formula.
Sobre alfa o PX.
X is canceled. That's it. Do it here. What am I doing? Not PX, this is income. You guys should have caught that. Okay. So that's income elasticity. What do we have left of the three elasticities we talked about of demand? Cross price elasticity. Okay. So this is actually kind of a trick question. I need the demand for, I need to do this, and if I remember right, I use PY. Might use PG. What's the first thing we do?
Es la parcial, pero no tenemos, sería cero, porque, o menos.
Perfect. As I said, it's kind of a trick question. So the partial with respect to PY is 0. So since the partial is 0, right, I multiply that by PY over X and I get 0. So the cross price elasticity of demand in this case is 0, simply because there's no other price in that Marshallian demand formula that we derived. Okay. Here's a much simpler Marshallian demand formula. And I'd like you guys to go ahead just in your notes and derive all the elasticities, the home price elasticity, income elasticity, and cross price elasticity. So it's the first one. And what's it going to be? Okay. Actually, let me write it out over here. Have X is equal to A minus B dx plus C Y plus D times I. So what's our own price elasticity of demand? Multiplicado por sobre X. Perfecto. Okay. So that's our own price elasticity. Negative B over Px over X. Negative B over Px over X. So income elasticity is going to be partial, right? X with respect to I, which is, I know you guys want to say it, come on.
Sure.
Right?
Sure.
D. That's a partial. It's basically the derivative of holding all sort of stuff constant, just D. Right? Times I over X. So I got DI over X. There we go. And that's our income elasticity. Right. If D is positive, it's normal or superior good. Of course, superior good has to be greater than 1. If D is negative, it's an inferior good. Okay. Cross price elasticity. We have a PY in this Marshallian demand formula. So the partial of X with respect to PY is C. Okay, so it's C times
Y.
PY over X. Perfect. You guys are on it, or at least some of you are. Some of you are just quiet, right? But you're understanding. Okay. So here we have C times PY over X. Right? It's a partial times whatever we're talking about, PYI or PX, over the quantity demanded, in this case, X. Questions? And if C is positive, it's substitute. If it's negative, it's a complement. And of course, with 0, they're independent. Questions on elasticity?
El rate of change o la pendiente de la derivada de todas estas unidades con respecto a X es la constante que tiene de frente.
It's, yeah, basic calculus. It's just, I take the derivative, holding everything else constant, and that's a partial. And then,
Esto depende de la función, o sea, tienen que aprender que es una derivada parcial, porque esa función te la pueden cambiar.
No, pero por eso, en ese ejemplo en específico, pues es bastante straightforward.
See, and that's why I gave you the Marshalling demand function at first. I know the cross price is tricky because it doesn't have a PY. But that's basically it. You take the partial, you get the slope. In this case, the slope is straightforward because it's linear. And then you multiply it by P equals PY. And if I give you numbers, then after you do it, you just substitute in the numbers.
Como es una ecuación lineal, sabemos que el slope coefficient es el cambio ahí. Como tú dices, la gente, si cambiara exponencial o algún logaritmo, pues ya.
Now, if I didn't give you a formula, and I just gave you, look, price increase by this much, right? Or price increase by this much, and then cause demand to decrease by this much, right? In that case, you calculate the percentage change, and just tell me the percentage change in price over, I'm sorry, the percentage change in quantity demanded over the percentage change in price. But if I give you a formula, right, you go through and you find the variable, you find the partial with respect to that variable, that gives you the slope, and then you just multiply that by whatever it is, Py over x, Px over x, y over x. Oops. Okay. Now we're going to change gears. That's the theory of the consumer, theory of the consumer. I call it utility theory, but we left utility theory and went into demand. So the theory of the consumer, now we're going to move on to the theory of the firm. So basically, just like we did with theory of the consumer, I'm thinking about a decision maker, an agent, in this case, the firm or the manager of the firm, who has goals, faces constraints, limitations on the ability to achieve those goals. So I'm trying to describe some constrained optimization process, right? Which means I'm trying to get the goals given the constraints I have, right? So that's going to tell us something about the behavior of the firm. Then once we have the basic ideal, I can see what happens when I change certain variables. So I change the constraint. In this case, it's going to be technology constraints for the most part. Or I change it how much we're able to spend on the product or price of inputs, for instance. So in the case of the consumer, they have preferences and utility, and they face a budget constraint. We asked, what were the changes of behavior due to a change in the budget constraint? We're going to use the same methodology for the firm, right? In fact, mechanically, it's almost identical, but we're talking about the firm instead of a consumer now. The firm can operate in different environments, which we'll talk about after the first midterm. Perfect competition, monopoly, oligopoly, monopolistic competition. Within some of those environments, we want to talk about how a change in our constraint, the limitations, could lead to change in behavior. Right? We asked, for example, if a change in the price the firm pays for its inputs changes, how does that change what the firm chooses to do? How does that change the quantity that it chooses to produce, and how does that change the price it charges for its output? Okay, so our constraints. So the constraints a firm has will have something to do with the environment, what market it's in. For example, pricing opportunities, technology. That's going to be our big constraint for most of our examples. And reactions to other firms when we talk about oligopolies. Changes in technologies are things that can change the firm's constraint. Okay. The goals. For a firm, there can be multiple goals. Basically, for the consumer, we assume the goal was utility maximization, maximize the satisfaction from consumption. For a firm, we have different possibilities. It can be cost minimization, revenue maximization, sales maximization, or what we'll assume for the most part, profit maximization. The example I give for cost minimization is Glen Urbano. Right? The train, it can be, its objective might be not to maximize profits, but to provide a certain level of service, subject to not making a loss, or providing a certain level of service at the most or the least expensive way possible. Right? So those are some possible objectives or goals for a firm that's not a profit maximizer, in this case, a cost minimizer. We have all kinds of possible models, and each will be relevant depending on what we're talking about. So behavior. We'll be asking questions such as, how does a firm produce? What price it charges, and how many inputs does it buy? And that leads us to our technology, right? For the consumer, we had a utility function, right? We made it up. For the firm, we're going to have something known as a production function. It's less abstract because we can actually observe what the firm does and what comes out. Right? So a production function is just a function that states the relationship between a set of inputs the firm uses and the output it produces. In the case of the consumer, like I said, we have the utility function, and production functions are going to be similar to utility functions. In fact, they're going to have a lot of the same characteristics that we talked about, like diminishing marginal returns. Instead of diminishing marginal utility, we are going to have diminishing marginal product. Instead of diminishing marginal rates of substitution, we're going to have something known as diminishing marginal rates of technical substitution. Graphically, mathematically, it's pretty much the same. Conceptually, it's different. Okay. So the utility function allows us to derive the utility function as goods consumed, while the production function allows us to derive a level of production from a given level of inputs. That is, output is some function of all the inputs we use. In this case, we have n inputs, x1 through xn, and that gives us an output. But just like utility, it's much easier to work with two goods. So in general, that's what we're going to be working with. Two inputs in this case. You remember we had a Cobb-Douglas utility function. Well, this is a Cobb-Douglas production function. And this is actually originally what Cobb-Douglas did. There were two economists back in, I think, in the 50s. And they basically looked at different firms and the relationship between capital and labor. And they took the data they collected and they gave it a functional form. And it looks like this, right? Output, Q. Oh, I'll do it right here. Output, Q, is equal to capital to some exponent, they called it alpha, times labor times some exponent, they called it beta, right? So that's a Cobb-Douglas production function. And just like with the utility and pretty much everything else we're going to do in this course, we can learn a lot by analyzing this at the margin. In other words, what that added input does to production, or utility, that added consumer good did to utility. Right? So that leads us to marginal product. And marginal product is simply the added production gain from increasing one input. I increase one input by 1 unit, that gives me my marginal product. It's similar to marginal utility, right? We saw it, you increase the amount of cake that you consume, how much more utility do you get from that 1 unit of cake that you consumed? Here, it's how much more production do you get from that extra input you added to production. So the marginal product of capital we denote as MPK is simply the partial of Q with respect to K, and I'll denote that by F of K. The marginal product of labor, MPL, is the partial of Q with respect to changes in labor, and I'll denote that by F of L. Okay. That brings me to diminishing marginal product. Just like we had diminishing marginal utility, here we have diminishing marginal product. And for the most part, we're going to assume diminishing marginal product in the same way we assume diminishing marginal utility. What this means is I can add more, when I add more inputs, production might go up, but production is going to go up for each unit of input that I add less than the unit of input added before it. So the 10th unit of inputs might add 100 units of output. The 11th unit of inputs is going to add less than 100 units of output in that case. And that's diminishing marginal product. What this means is we add more inputs, production may go up, but the last unit of input adds less to production than the unit before it did. What this means is the first derivative or a production function could be positive or can be positive, and almost certainly most of the time will be positive. But the second derivative, at least after some point, is going to be negative. And that's what we have here. The partial of the marginal product of capital with respect to capital, right? It's the second partial of Q with respect to K. That's going to be negative. And the same thing for labor. Our second derivative is negative. In other words, it's increasing, but at a decreasing rate. So if I have something on the margin, I can have something that's average, right? We didn't talk much about average utility because it really didn't help us much. But when we're talking about production, things we can measure, it's harder to measure marginal product than it is average product. So we work a lot with average. So the average product, for instance, of labor, APL, is simply my total amount produced, which is derived from the production function divided by L. So it's Q over L, or my total production function over L. Same thing for the marginal product of capital. It's Q, my total production, over K, or my production function over K. Questions? Okay. So having said that, that leads me to something known as an isoquant, right? Just like we did for utility theory, I can think of two inputs and production being the third axis on a three-dimensional graph instead of utility, where I add more and more of those two inputs, I climb the mountain. And then basically I cut a piece of the mountain off at a certain elevation, and that gives me a certain level of production with different levels of inputs, just like my indifference curve did for utility theory. So I got the same utility along the indifference curve. Now we're going to talk about something known as an isoquant that mechanically is the same thing as an indifference curve. So I'm going to go ahead and derive it a different way. Say I have a single output and two inputs, Y1 and Y2. So I might want to look at the combinations of the two inputs that produce the same level of output. Say at point A, below there are two ways I can produce, let's say, an omelet. Each uses different proportion of eggs and labor, right? And you beat it or however it is. One uses a relatively smaller amount of eggs and more labor than the other one. So here it is. I have Y1 and Y2. I can think of Y2 as eggs and Y1 as labor. So I have two ways to make the omelet. I mean, either add more labor or add more eggs. I might want to assume constant returns to scale, which means that I can produce anywhere along the ray from the origin, right? Basically, a ray is just a straight line. So I start at the origin, I run a straight line through those 2 points, right? And call those rays. So my technology now is describing a production set that consists of the 2 rays. I can produce anywhere along those rays. I just have to add or subtract labor or eggs. And these arrows, they don't mean anything. They're just pointing to one omelet. Those 2 dots are producing one omelet. I might want to also assume concavity. Convexity, not concavity. This would mean I can produce one omelet using a linear combination of the two techniques. In other words, I can produce half an omelet using one technique and then another half using the other technique, put them together, and I get one omelet. That is assuming I have additivity. I can produce one omelet producing half an omelet one way, half an omelet another way. Or I can produce a whole omelet using a convex combination of the two techniques. In other words, I draw a straight line between them and I produce one omelet. So, or I can produce half and half, right? And both give me the same results. That's one omelet. Next, I want to add something known as free disposal. In other words, all that means is it doesn't cost me any more to use more of the good. I still produce one omelet. And if I throw away the stuff that I didn't use, it doesn't matter. So basically, I get to produce one omelet here, but if I use more labor, I'm still producing just one omelet. Or if I add more, if I add more eggs, I'm still producing just one omelet, right? So I can add, in other words, I can add arbitrarily more of factor 1 or factor 2, and I still get one omelet. If I had 3 different ways of producing the omelet, by taking a convex combination, I get the following. And notice it's starting to look a lot like what we had in difference curves. But we're not going to call this an indifference curve because it's production. So I'm going to produce a convex hull from all the different activities that are available to me to produce that one omelet. I have several ways of producing the omelet. The lower hull is going to be the most efficient ways that I can produce that single omelet. So in general, if I have lots of different activities, ultimately I end up with a convex surface like the one in the next graph, figure F, and we'll call that a unit isoquant. We call it a unit isoquant simply because I'm producing one, right? But in general, it's just an isoquant. Right? Well, I get this convex hull, right, with Y1 and Y2. And like I said, it looks a lot like a difference curve that we worked with in utility theory. But this is production. This gives me all the different combinations, the efficient combinations, to produce one omelet with my 2 inputs. So in general, the isoquant depicts a situation, right, where the same level of production can be achieved using different combinations of inputs. So here, along this isoquant, the different combinations of input produce 100 units of output. Along this one, they produce 150 units of output. Okay. So notice this isoquant looks like a lot like an indifference curve, as I mentioned 2 or 3 times already. The difference here, we're analyzing production, while before we're analyzing utility. Of course, the indifference curve is derived from the utility function, where the isoquant is derived from the production function. Okay. So now that we have an isoquant, I want to look at the change between the 2 inputs, or in other words, the slope of the isoquant. For the indifference curve, we call it the marginal rate of substitution. Here we're going to call it the marginal rate of technical substitution. So the marginal rate of technical substitution is simply the rate at which the firm has to substitute one input for another while keeping production constant. Right? In other words, it's the slope of the isoquant. Again, it's a very similar concept to the marginal rate of substitution in utility theory. So here it is. It's the slope, right, of the isoquant holding utility constant. Now, if I take my production function sorry about that. what I want to do is, the first day of class, I introduced partials. And if you remember, I introduced something known as a total differential. All a total differential is taking all the partials one at a time and then adding them up. And then multiplying it by the change in that variable. So originally I'm going to have the partial dq. I'm going to have the partial of my production function with respect to L times a change in L, dL, plus the partial of my production function with respect to capital, plus the change in capital, dk. Right? Now this is the change, the partial of F with respect to L is simply the marginal product of labor. The partial of F with respect to K is simply the marginal product of capital. So I can rewrite that as a marginal product of labor, dL, plus the marginal product of capital, dk. Right? Preguntas? Since I want to stay on the same indifference curve, in other words, production doesn't change. I'm sorry, indifference curve. I said indifference curve. Not what I meant. Isoquant. I want to stay on the same isoquant, right? What that means is my change in quantity that I produce is 0. So dq is 0, so I set this equal to 0, and then I can go ahead and solve for dk dl or dl dk, depending on what you put at what. So I set it equal to 0, and I get the marginal product of labor, dl, is equal to negative the marginal product of capital. And I solve for negative dk dl, the slope of the isoquant, and that's simply going to be equal to the marginal product of labor over the marginal product of capital, which we denote as our marginal rate of technical substitution. Again, similar to consumer theory, where the marginal rate of substitution was equal to the ratio of marginal utilities. Here, the marginal rate of technical substitution is equal to the rate of marginal products. In this case, the marginal product of labor over the marginal product of capital. Questions? Okay. So now, if you remember, in utility theory, we went from diminishing marginal utility to diminishing marginal rate of substitution. We do the same thing here. Usually I do it with a lot of algebra, as you see, but I'm just going to skip ahead because we've already done this with utility. Right? I just take the derivative, the marginal rate of technical substitution with respect to labor. We can do the same thing with capital. Right? I take the derivative here with the quotient rule. Once I get that, I do a bunch of algebra and manipulation, and you're not going to be held responsible for that. And we see that the change in the marginal rate of technical substitution with respect to labor is negative. How we see that? Well, let me go back a second. We assumed from our diminishing marginal product that the second derivative with respect to labor is negative, and with respect to capital also negative. But the first derivatives were positive. And here, I'm going to assume, and this is known through something as Young's theorem, f of Lk is equal to f of Kl. So I can just put those together. And I'm going to assume that the cross product is positive. And we can actually prove that. I don't really have to assume it, but I'm not going to do it. Just too much math. So f of k squared is positive, f of fl is negative. This first part of the numerator is negative, 2 is positive, f of k is positive, f of l is positive, f of kl is positive, but I have a negative sign in front of all this, so The second element in the numerator is negative. F of L squared is positive, F of KK is negative, so this third element in the numerator is negative. And of course, F of K cubed is positive. So I have negative, 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 making this negative, which means that the marginal rate of technical substitution with respect to labor, and we can do the same thing with capital, is negative. And what that gives me is diminishing marginal rates of technical substitution, in the same way that diminishing marginal utility gave me diminishing marginal rates of substitution. Okay. Questions? Okay. So that concept allows us to examine what happens to production when all inputs are increased by the same percentage. When I say that, I mean returns to scale. So if I increase all my inputs by 10% and my output increases by 10%, I have constant returns to scale. If I increase all my inputs by 10% and my output increases by less than 10%, I have decreasing returns to scale. And if I increase all of my inputs, right, and my output increases by more than 10%, I have increasing returns to scale, right? In our Cobb-Douglas production function, and it's really not that important, but when we write it out, right, in the following way, okay, if alpha plus beta is equal to 1, we have constant returns to scale. If it's greater than 1, we have increasing returns to scale, and if it's less than 1, we have not important, just an interesting excuse me, an interesting element of the Cobb-Douglas production function. Okay. Questions? The next thing I want to talk about is something known as elasticity of substitution. Remember, we talk about marginal products, we talk about one input at a time, we talk about constant returns to scale. It's both inputs at the same time. So elasticity of substitution measures proportional changes in both inputs, or the ratio of inputs, in this case capital over labor, relative to the proportional change in the marginal rate of technical substitution along the isoquant. So we call it sigma. It's basically the percentage change in the ratio of inputs divided by the percentage change in the rate of technical substitution. I don't know why your book did this here, but I kept it the same. It's a change in the marginal rate of technical substitution. They just left out the M for some reason. I kept it. So it's a change in K over L over the change in the rate of technical substitution times the marginal rate of technical substitution over K over L. So it's just a partial of the log, and this is just algebraic, the natural log of K over L over the partial is the marginal product of capital over the marginal product of labor. And that's just an algebraic, how should I say it? It's the word I'm looking for. It's just something that happens with algebra when we apply the natural logs. Okay. Technical progress. I'm just going to talk about this very trivially, and then we're done with the lecture for today. With improvements in the production process, more output can be obtained with the same combinations of inputs. I can represent this with the parallel shift in the isoquant. I can denote this mathematically by putting a shift in the parameter A of t. That's a shift parameter. And that denotes technology over time, or maybe learning over time. Since I assume technology will improve with time, I can write this and all other variables as a function of t, Notice T denotes time. Now, unlike before, when it was simply a random parameter. So I have this times a production function. And that's pretty much it. This is basically something that, depending on who teaches macro, you will probably cover in macro. So I'm going to leave it for macro. For now, I'll let you guys get better at algebra, because it gets ugly. But that's it. Okay. Questions? Okay. As I said, I was going to have a short lecture, partly because I was skipping some stuff and went over some stuff fast. Okay, today we covered what was known as the isoquant. Next week we're going to cover isocost. The isoquant looked a lot like the indifference curve. The isocost curve is going to look a lot like the budget curve. So, but in this case, right, before we had a given budget and we got to the highest indifference curve that we could. Here we're going to have a given isoquant and we're going to move the isocost down. We're going to find the cheapest way to produce it. So, in other words, instead of moving the indifference curve or moving the higher indifference curve, we're going to be lowering, we're going to have a fixed isoquant, and then we're going to move to lower isocost until we get to one that's just tangent that'll give us, that'll produce that level of output at the lowest cost. And that's what we're going to do next week. The week after that, we're not going to do this next week because I'm not going to see you guys next week. But the week after that, we'll see it. And the week after that, we'll go through and we'll do some problems in theory of the firm. I covered theory of the firm a little faster, so therefore I devote one class to just going over problems on theory of the firm, and that's what we'll do. And then after that, or on that day, we'll talk about when we're going to have the first midterm. Questions? Perdona?
Maximization.
It's optimization, but yeah, in this case, we are going to have a fixed isoquant, and we're going to get to the lowest isoquant, in other words, the lowest cost of those two inputs that we can. So where it's tangent to our isoquant, and our isoquant here we saw in general is going to be convex, right? Just like our indifference curves. Questions? More questions? Okay. How are you guys doing with your other classes? Easier than this one? Okay. All right. Then I'll see you guys in 2 weeks. I would like that next Wednesday. I know you guys are free and you're going to be tired after work or whatever, but I'd like you to go through and study. Maybe if you haven't done that first homework assignment, to do it. You get the practice in. That way, when you come for the test, you have a better understanding of what we're doing and where we're at. La mayoría va a ser problemas. I'm gonna try to make it. Well, I haven't really looked at it. It's possible that I'll make it more quantitative than I have in the past. But I haven't really looked at it. Or thought about it. All right. Have a nice weekend, or have a nice 2 weeks, and I'll see you a week from Wednesday. You too.